So there's a qualitative difference between time and space variables, and correspondingly we use different language for them. So constraints for u for certain values of t, the time variable, are called initial conditions, or ICs, and most of the time these are given when, or ICs, and most of the time these are given for, or ICs, and most of the time these are given for when time is equal to 0. Then constraints on the state variable for certain values of x and y, the spatial variables, these are called boundary conditions, or BCs. And so boundary value problems are different from initial value problems. Whoops. And so I mean that qualitatively. So for example, the usual existence and uniqueness theorems don't hold. And we'll talk more about that later when we look at these in detail. But for now, let's look at an example of how these conditions work. So let's look at a bar that goes from minus L to L, and we'll consider the heat equation. So we'll take this to be our domain, and the boundary of this is just the 2 points, one at minus L and one at L. So that's the boundary. And if we specify the value of u on the boundary, this is referred to as Dirichlet boundary conditions, and the resulting problem would be a Dirichlet problem, as opposed to, say, specifying the value of the spatial derivative u sub x on the boundary. That's an example of, that would be called Neumann boundary conditions. Okay, so let's suppose we have the domain where x is between minus 4 and 4, and t is supposed to be strictly positive. So in our domain like this, let's see, so we're going to look at the heat equation, and this is, let's see, so we'll have x going in this direction and t going in this direction, and let's change colors here, and so we'll have over here at minus L, we'll have a condition, and over here at L, we will have a condition. And let's see, so we've got the beginning of the interval right here, and this region right here is going to be the domain on which the PDE needs to be satisfied. Sketch that in a little bit there. Okay. All right, so we want to solve the heat equation on this domain, and maybe we will give an initial condition of, say, ux0 is e to the minus x squared. So that's going to look something like this bell curve. That'll be over the red line right here. And then, so that's, oh, sorry, I forgot to specify, that's the initial conditions. And then we also have the boundary conditions. And for this, we'll just say that u at -4 for all time will be equal to 0, and also that u at +4 for all time will be equal to 0. Now, these functions here don't need to be constant. In this case, they are constant. But they don't need to be. However, they do make things a lot simpler when they are constant. And so then the resulting solution to this differential equation would have a surface that looks like this. So here you can see this is where time is equal to 0 right along the front. There's our initial condition, the red bell curve, and then at either end of the interval, so at -4, we've got this line coming up the back. At +4, we've got this line coming up the front. And the value of the function u is fixed to be equal to 0 along each of those green lines, just like we required. And then it turns out that this thing I've sketched in orange is, or plotted in orange, is the actual solution for the heat equation right there. And I don't really want to call out too many points about it, but if you notice right here, you can see this kind of exponential decay coming down towards 0 from each of these right here. The other thing maybe you want to notice is that I've got sketched in purple here what it looks like when, oh, actually here, let me draw it. So this is where time is equal to 0. This might be where time is equal to 1, and this might be where time is equal to 2, sketched in purple there. So each of those purple curves is like a time snapshot of what the heat profile looks like in this bar.